Okay, in today's lecture, we're going to cover the second part of the section 6.2 material on properties of power series. And in this second half of the lecture, we're going to discuss primarily how to differentiate or integrate power series and look at some applications. So let's start by introducing the following theorem on differentiation and integration of power series. So here's what our theorem says. If we have a power series representation of some function f of x as a power series centered at a, so that is the sum from 0 to infinity of some coefficient c sub n times x minus a to the nth power, and this power series has a radius of convergence r, which is positive, then we can differentiate or integrate this power series in the following way. So part one of this theorem tells us how to find the derivative of that function, f prime of x. So essentially this theorem is saying that we can differentiate term by term. So if we look at the expressions within our power series, we're going to have the same coefficient c sub n, and then the derivative of x minus a to the nth power would be n times x minus a to the n minus 1 power. So we're just using the power rule to find our derivative there. And now notice one thing that's a little bit tricky here. Our initial value for the sum of, or in this summation, was n equals 0. And here when we took our derivative, this is changed to an n equals 1. So we were increasing the starting value of that index by 1. Now why do we need to do that? Well, to illustrate, let's think about writing this out in a little more detail. Here, the function f of x that we're considering has a power series representation, sum from 0 to infinity, of c sub n, x minus a to the nth power. So if we were to write this out, or write out the first few terms of this series, we would have c0 plus c1 times x minus a to the first, plus c2 times x minus a squared, plus c3 times x minus a cubed, and so on. So if we take the derivative of this function, f prime of x, this theorem says we can take our derivative term by term. So starting with our first term, c naught, which is a constant, well, the derivative of a constant is 0. Then for our next term, the derivative of c1 times x minus a gives us c1 times 1. For our next term, we have c2 times x minus a squared, so the derivative would be c2 times 2x minus a to the first power. Then plus our next term was c3 x minus a cubed, so the derivative will be c3 times 3x minus a squared, and so on. So because this initial term in our power series representation was a constant, c naught, when we took our derivative, its derivative was 0, and so now for the derivative of our function, f prime, the first term that appears is c1. So if we're using a coefficient of cn, we now need to start the series at 1 instead of 0, so that the first term corresponds to c1. Now, in some of the examples that we'll consider, along with some of your homework problems, we sometimes want to force our power series representation of the derivative to start at n equals 0 instead of n equals 1. And to do that, we can just make a change of that index variable. So if I force this to start at n equals 0, that is if I decrease the starting value of my index by 1, then in the general term that we had for our series, I have to replace all of my n's by n plus 1. So we end up having c sub n plus 1 times n plus 1, and then times x minus a to the nth. So if we write out the terms of those series, we can see that they represent the same function, f prime here. Now the second part of this theorem says the following. If we want to integrate or find the antiderivative of our function f of x, which was represented as a power series, we would again do it term by term. So we would have here the sum from 0 to infinity of our coefficient cn, just some constants, and then the derivative of x minus a to the nth power, using the power rule, is x minus a to the n plus 1 divided by n plus 1. And then since this is a indefinite integral, we need to include a constant of integration, some plus c, where c is an arbitrary constant. And normally we would write the constant of integration out in front of the summation, just to be clear that the constant c isn't being added infinitely many times. That way we don't think it's part of that summation. And now one last result as part of this theorem. This theorem says that the radius of convergence for both of these power series, that is the power series representing f prime and the antiderivative of f, is r. That is, these will have the same radius of convergence as the original function, f of x. Now, that only refers to the radius of convergence, not necessarily the interval of convergence. So if we have a function f of x where maybe the interval of convergence is a closed interval, so maybe we include both endpoints, then when we differentiate or integrate, we might have to throw out one of those endpoints for the interval of convergence of, say, the derivative. But the radius of convergence for those series will be the same. So now that we have a method for differentiating and integrating functions represented as power series, let's look at an example. So in this first one, we have f of x is this power series, sum from 0 to infinity of n plus 1, x to the n over n factorial. And we are asked to find both the derivative and antiderivative of that function. So let's start by looking at f prime. F prime of x, using our theorem, says we can differentiate term by term. So I'm going to have the sum from n equals 1 to infinity. Remember, we have to change the starting value of our index to 1 when we differentiate. And we would have our coefficient, which was n plus 1, divided by n factorial. And then the derivative of x to the nth is n times x to the n minus 1 power. So we have the following, and we can simplify this a little bit. If we reduce the quotient n divided by n factorial, let's see what we have. So here we would have the sum from 1 to infinity of n plus 1, and then n divided by n factorial leaves us with n minus 1 factorial for our denominator. And then we still have this x to the n minus 1 power on the end. Now, if we were to want to rewrite this expression for f prime as a power series starting at 0 instead of at 1, we could do that. So this would be the same as the sum from 0 to infinity of n plus 2 divided by n factorial times x to the nth power. So this would be a power series expression for the derivative of our function starting at n equals 0. Now the second part of this question asks about the antiderivative of f of x with respect to x. So our theorem says, well, we can integrate our power series term by term, and since this is an indefinite integral, we know that we need to include our constant of integration. So I'm going to write that out in front of my series, and then I am adding the antiderivative of each term. So we have the sum from 0 to infinity of our coefficient, which was n plus 1, divided by n factorial, and then the antiderivative of x to the nth power becomes x to the n plus 1 over n plus 1. So we see here that to simplify, we could cancel a factor of n plus 1 on top and bottom, and we are left with a constant of integration plus the sum from 0 to infinity of x to the n plus 1 divided by n factorial. So this would be a power series representation of the antiderivative. Now, if we knew what f of x was, or what this antiderivative was, I might be able to solve for my constant of integration c. But here, since f is an arbitrary function in terms of this power series, we have to leave that constant of integration as is. But we'll see some other examples later in this section where we can solve for that constant. So let's look at some other ones. In our next example, we are asked to evaluate the following antiderivative as a power series. So one application of representing functions as power series is to integrate functions which can't be integrated using any of our other techniques. And this is an example of such a function. This integrand, x divided by 1 plus x to the fifth, cannot be integrated by a substitution, integration by parts, using a trig substitution or partial fractions. So none of the techniques that we have for this course allow us to find an antiderivative of that function directly. But if we can express this function as a power series, then using our new theorem to integrate it, we could integrate each term of our power series. So let's see what we would have here. Our first step is to find a power series representation of this integrand. So let's start by taking a look at it. So we have the function x over 1 plus x to the fifth. And if I want to rewrite this in terms of a power series, I could make use of the formula for the sum of a geometric series, the same sort of concept that we were using in the first part of this section. So I could think about this as x over 1 minus negative x to the fifth, and this now has the general form a over 1 minus r. It looks like the formula for the sum of a geometric series, where we would go from 0 to infinity, a times r to the nth power. So I can rewrite my integrand, that is x over 1 plus x to the fifth, as a geometric series, the sum from 0 to infinity of a, which was our numerator, in this case x, times r. So here we have 1 minus r. We were subtracting a negative x to the fifth. So I'll have negative x to the fifth, quantity raised to the nth power. And recall that I can do this provided that the absolute value of my ratio r, in this case negative x to the fifth, is less than 1. Okay, so in order to integrate this, we might first want to simplify the expression that we have for our power series. We'll see throughout this section and the next section that if you're going to find a derivative or antiderivative of a power series, it is very helpful to first simplify it. So for the power series that I found, one way that I could rewrite this would be as negative 1 to the nth times x to the 5n plus 1. So here, using properties of exponentials, if I had negative x to the fifth raised to the n, well, I can split that up as negative 1 to the n, and then x to the 5n, and that extra factor of x I had out in front makes this 5n plus 1 power. So we represent our function in terms of this power series. And now to integrate it, that is to integrate x over 1 plus x to the 5th with respect to x, well, we're looking at integrating this power series representation. So here we have an indefinite integral, so we know that we need to include a constant of integration in c, which we'll write out in front. And then we have the sum from n equals 0 to infinity of negative 1 to the nth power. And then the antiderivative of x to the 5n plus 1 is x to the 5n plus 2 divided by 5n plus 2. So we have the following expression for the antiderivative of this function in terms of a power series. So we don't know what the function is as a simple function of x, but we can express this antiderivative in terms of a power series centered at 0. Now we might ask ourselves, well, when would this be a valid representation of that antiderivative? So remember here that part of our restriction is this is only true if the absolute value of negative x to the 5th is less than 1. So simplifying that inequality, well, we would have the absolute value of x to the 5th has to be less than 1. And then taking a 5th root, we find the absolute value of x has to be less than 1. So for this example, our radius of convergence would be 1. All right. So let's look at some other examples where we'll have some more applications of differentiation or integration of a power series. So in this next one, we are asked to find a power series representation of each function and determine its radius of convergence. So in part A, we have the function f of x is 1 over 3 plus x quantity squared. Now, if it was just 1 over 3 plus x, I could rewrite that ratio in the form of the sum of a geometric series. That is the form a over 1 minus r. But in this example, we have that quantity in the denominator being squared. So we can't make use of that formula for the sum of a geometric series with the function in this current form. So let's think about what we could do to decrease that power of 2 in our denominator to something to the first power. So one way which I could decrease that power is by integrating this function. So to start here, let's define a new function, capital F of x, as the antiderivative of this function, little f of x, which is 3 plus x to the negative 2 power, integrating with respect to x. So if we find this antiderivative by using a substitution in the power rule, we have the antiderivative is some constant c minus 1 over 3 plus x to the first power. So this function that I have after my constant, 1 over 3 plus x, this function I can rewrite in terms of the sum of a geometric series. So I could find a power series representation of this function, capital F. Let's see how to do it. So here, our function, capital F of x, was given by some constant c minus 1 over, if I factor out a 3 from the denominator, I'm left with a 1 plus x over 3. So I could rewrite this as some constant c minus 1/3 divided by 1 plus x over 3, or 1 minus a negative x over 3. And this now has the form of the sum of a geometric series, a over 1 minus r. So we can rewrite this as some constant c minus the sum from n equals 0 to infinity of a, which is 1/3, times our ratio, which is negative x over 3, raised to the nth power. And I can do this as long as the absolute value of that ratio, negative x over 3, is less than 1. So now, before I work backwards to try to get a power series representation for the original function that I was given, let me rewrite the expression that I have for this power series. So I'll have a constant c, and I'm going to rewrite this in the following way. I'll write it as plus the sum from 0 to infinity of negative 1 to the n plus 1 times x to the n all over 3 to the n plus 1. So what I'm doing here to rewrite that is making use of properties of exponentials. So in my numerator, this negative x to the nth, I can rewrite as negative 1 to the nth times x to the nth. And then the extra factor of negative 1 that I had out in front, if I bring that inside of my series, this becomes a positive term. And then that extra factor of negative 1 makes this negative 1 to the n plus 1 power. And then my denominator was 3 to the first times 3 to the nth. So I get 3 to the n plus 1 for my denominator. So what I have found here is a power series representation of the antiderivative of the given function, capital F of x. So if I want a power series representation of the original function, little f of x, well, I know that little f of x would be the derivative of its antiderivative, that is capital F prime. So if I were to differentiate the power series that we just found, well, our constant of integration c out in front has a derivative of 0. And then differentiating term by term, we would have the sum from n equals 1 to infinity. Again, remember when we differentiate, we've got to change that starting value for our index. And we have negative 1 to the n plus 1 divided by 3 to the n plus 1 power. And the derivative of x to the nth is n times x to the n minus 1 power. So we see here, if we wanted to rewrite this as a power series starting at n equals 0, we could shift that starting value of our index. Let's make this the sum from 0 to infinity of negative 1 to the n plus 2 times n plus 1 times x to the nth all over 3 to the n plus 2 power. So this would be an expression for the power series expression for the function that we were given here, f of x. Now, we were also asked to determine the radius of convergence for this power series. So let's think about what restriction we had. We saw that we could only write the antiderivative, capital F of x, as a power series if the absolute value of negative x over 3 was less than 1. So solving that inequality, we find the absolute value of x over 3 has to be less than 1. So the absolute value of x has to be less than 3. So that implies the radius of convergence is 3. So that gives us an idea of the interval where we could represent this function f of x in terms of that power series. So let's look at some other examples. In part B, we have something pretty similar. We've got f of x is x squared over 1 minus 3x quantity squared. So again, what's making this a little tricky is the fact that our denominator is being squared. I can't immediately write this in the form of the sum of a geometric series. So instead, we can try to make use of the same thing that we did in part A. So my function f of x, if I were to factor an x squared out from the numerator, I would be left with 1 over 1 minus 3x quantity squared. So that is x squared, and now this function in square brackets, I'm going to call little g of x. So here, my function f of x that I'm given is of the form x squared times a function g of x. And this function g of x that we're working with is almost identical to the type of function that we saw in part A. So let's see if we could handle that g of x function the same way that we did in the previous example. So in order to put it in the form of a geometric series, or the sum of a geometric series, I'm going to let capital G of x denote the antiderivative of g of x. So that is the antiderivative of, we had 1 over 1 minus 3x squared. That's the same as 1 minus 3x to the negative 2 power dx. And that antiderivative, if we make use of a u substitution in the power rule, we have some constant of integration plus 1 over 3 times 1 minus 3x to the first power. So you might ask, well, where did this extra factor of 3 come from out in front? It comes from the fact that we're making a substitution here where we would let u be 1 minus 3x. So our du is negative 3 dx. So we're picking up an extra factor of 1/3 here when we make that substitution. So this function that I have can now be expressed as some constant c plus 1/3 over 1 minus 3x. And this function, following my constant of integration, now has the form of the sum of a geometric series. So this capital G of x function, that is the antiderivative of little g of x, can be written in the following way. We have a constant plus the sum of a geometric series. And our series would be of the form from 0 to infinity, a, which was 1/3, times r. So here we had 1 minus 3x. So 3x is our value for r. We're raising that to the nth power. And we can do that, again, if the absolute value of this ratio, 3x, is less than 1, or equivalently, if the absolute value of x is less than 1/3. So before trying to work backwards to find the function little g of x, let's simplify the expression that we have for capital G. So we would have a constant c plus the sum from 0 to infinity of, well, let's see how we can rewrite this. So I'll have 3 to the nth divided by 3. So that will leave me 3 to the n minus 1. And then I have x being raised to the nth power. So I've got the following expression for capital G of x, which was the antiderivative of little g. So to find the function little g of x, I would take the derivative of capital G of x. That is, the derivative of the antiderivative should give me back the original function. So if I differentiate this, well, the derivative of our constant of integration c is 0, And then differentiating term by term, I have the sum from n equals 1 to infinity of 3 to the n minus 1. And then the derivative of x to the n is n times x to the n minus 1 power. Or if I want to rewrite this as a series starting at n equals 0, I would have the sum from 0 to infinity of 3 to the nth times n plus 1 times x to the nth power. So what I found now is a power series representation of the function little g of x, which was given up here. But what I want is a power series representation of f of x, which is x squared times g of x. So let's write this out. Here, f of x is given by x squared times little g of x. So that is x squared times this power series that we just found for g of x. So what I can do here to simplify is take this expression for x squared and distribute it through to my series. So my x squared grouped with this x to the n power will give me x to the n plus 2. So I have for f of x the sum from 0 to infinity of 3 to the n times n plus 1 times x to the n plus 2 power. So this would be my power series representation for the given function f of x, and the radius of convergence of this power series is 1/3. We found that from our earlier work using the condition for a geometric series to converge. So in these first two examples, we see that if we have a function, if it's not immediately able to be expressed in terms of the sum of a geometric series, we might be able to integrate that function in order to put it in the appropriate form. And then once I find a power series representation for that antiderivative, I could take the derivative of that function to get a power series representation of the function that we started with. So in our next example, we'll look at something similar, but with a slightly different approach. So in part C, we have the function f of x is natural log of 2 plus x. And this certainly doesn't have the form of the sum of a geometric series. But what I could do with this function is take its derivative. I know if I differentiate logarithmic functions, that gives me a quotient, something of the form 1 over a function, and that starts to look more similar to the sum of a geometric series. So what I would do for this problem is first look at the derivative of our function, f prime of x. So here, the derivative of natural log of 2 plus x using the chain rule would be 1 over 2 plus x. And the derivative of the inner function is just 1. So we have the following for the derivative of our function. And I can manipulate this ratio to rewrite it as the sum of a geometric series. So what I could do here is start by factoring out a 2 from the denominator, and that would leave me with a 1 plus x over 2. And I could then rewrite this as a 1/2 over my 1 plus x over 2, we can think of as subtraction by negative x over 2. And now this has the form of the sum of a geometric series. So the derivative of our function, f prime of x, I can rewrite as the sum from 0 to infinity of a, which here would be 1/2, times r to the nth. And here my ratio r is this negative x over 2. So so raising that quantity to the nth power. I could rewrite this as the sum from n equals 0 to infinity of negative 1 to the nth times x to the n divided by 2 to the n plus 1 power. And I'm able to do that as long as the absolute value of my ratio, that is negative x over 2, is less than 1, or equivalently, if the absolute value of x over 2 is less than 1, or if the absolute value of x is less than 2. Now, once I have this f prime of x expression as a power series, I can integrate it to find the original function, f of x. So here, f of x would be found by integrating the derivative, which we found to be the sum from n equals 0 to infinity of negative 1 to the n times x to the n over 2 to the n plus 1 power. We're integrating with respect to x. So let's see what we have. Taking the antiderivative, we would have some constant of integration c plus the sum from n equals 0 to infinity of negative 1 to the n over 2 to the n plus 1, and the antiderivative of our x to the n term is given by x to the n plus 1 divided by n plus 1. So we have the following power series representation of our original function, but one thing that we want to be a little careful of here is that this power series is representing a specific function, the natural log of 2 plus x. So I don't want to include any arbitrary constant c to represent that function. I know that the power series has to have this form, but the question becomes what constant c would we need to add to get the specific function that we're interested in. So let's think about how to find that here. What we just found is an expression for f of x. So we can solve for our constant c if I were to use a specific initial condition. And let's think about what condition I want to use here. So to isolate c, I want to kill off all of these other terms in my series. And this power series is centered at x equals 0. So if I were to plug in 0 for x, I would have my constant c, and then x, if x is 0, every other term in this series is now 0. So we would have just the constant itself. Now, we know what the function is. In this example, f of x is log of 2 plus x. So plugging in 0 for x, we have the natural log of 2. So here, my constant c has to be the natural log of 2 in order to represent this specific function. So we find that f of x can be represented as the natural log of 2 plus the sum from 0 to infinity of negative 1 to the n times x to the n plus 1 all over 2 to the n plus 1 times n plus 1. So this would be our representation of the given function as a power series. And the radius of convergence here is 2. We saw from our earlier work this series is guaranteed to converge as long as the absolute value of x is less than 2. So now in the next example, part D, we have x times the natural log of 2 plus x. So in the previous part, well, we just found a power series representation for the natural log of 2 plus x. We're just multiplying it by x now. So here, to get or power series representation of f of x, we're going to take the expression that we had for our power series in part A and multiply it through by x. So we have the natural log of 2 times x plus the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 2 power now. So where does that power come from? Well, I had x to the n plus 1, and then remember I'm multiplying through by another power of x. So we get x to the n plus 2. And then the whole thing is being divided by 2 to the n plus 1 times n plus 1. So we would have the following power series representation of that function, and we would have the same radius of convergence, r equals 2. Now in part E, we are then asked to find a power series representation for the antiderivative of x times the natural log of 2 plus x with respect to x. So using what we just found in part D for the power series representation of that function, now we're just supposed to integrate it. So let's see what we have here. F of x would be the integral of the power series that we just found in part D. So that was natural log of 2 times x plus the sum from 0 to infinity of negative 1 to the n, x to the n plus 2, all over 2 to the n plus 1 times n plus 1 with respect to x. So integrating here, we would have our constant, the natural log of 2, times the antiderivative of x would be x squared divided by 2. And then for our series, we can integrate term by term. So we have here the sum from 0 to infinity of negative 1 to the nth divided by 2 to the n plus 1 times n plus 1. And then the antiderivative of our x to the n plus 2 with respect to x is x to the n plus 3 divided by n plus 3. And in general, this was an indefinite integral, so we want to include a constant of integration. So again, for series, we might write our constant of integration out in front. That way that we don't think that our constant c is included within that summation term. So we would have the following expression for the antiderivative of the power series we found in part D. Okay. So let's look at one other example. This next one will come into play a little more when we get into our next section of material. So here we have f of x is arctangent of x, and we're supposed to find a power series representation. So again, in this example, we have a function which cannot immediately be considered as the sum of a geometric series. But if I were to differentiate this function, I know that the derivative of arctangent x gives me a ratio, 1 over 1 plus x squared, which now can be rewritten in the form of the sum of a geometric series. I would have 1 over, instead of 1 plus x squared, I can think of this as 1 minus negative x squared. And this now has the form of the sum of a geometric series. So f prime of x here can be written as the sum from 0 to infinity of a, which is 1 here, times r, which is negative x squared to the nth power. And I can rewrite the series in this way, or simplify it, as the sum from 0 to infinity of negative 1 to the nth times x to the 2n, provided that the absolute value of my ratio, negative x squared, is less than 1. Or equivalently, absolute value of negative x squared is the same as the absolute value of x squared. So that needs to be less than 1. And then taking the square root of both sides, we find the absolute value of x would have to be less than 1. So in order to get a power series expression for arctangent of x, well, we have a power series for its derivative. So to get back to the original function, f of x, I would then need to integrate what I just found for f prime. That is the sum from 0 to infinity of negative 1 to the n times x to the 2n with respect to x. So since this is an indefinite integral, I have a constant c plus, integrating term by term, I have the sum from 0 to infinity of negative 1 to the nth, and the antiderivative of x to the 2n will be x to the 2n plus 1 divided by 2n plus 1. Now again, this power series representation that I found is for a specific function arctangent of x. So I don't want to just include any arbitrary constant out in front. I'm looking for some specific constant that will represent my particular function here. Now, in order to find that constant, we can again think about substituting 0 into this power series for x. Since this is a power series centered at 0, when I plug in 0 for x, I'm left with just the constant c. And I know that my function f of x is arctangent of x. So if I'm plugging in 0, I'm looking at arctangent of 0, which is 0. So my constant c has to equal 0. And so we find that our power series representation of this function f of x would be the sum from 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1. So this is a power series representation for the arctangent function. And this particular power series is given a special name. This series is what is called Gregory's series. And we can make use of this series to approximate the value of pi, or to express pi in terms of the sum of an infinite series. So if we make use of what we know about the value of tangent, let's take a look at it down here. I know that arctangent of 1 is equal to pi over 4. So if I look at my power series representation for the arctangent function, and I'm plugging in the value x equals 1, then this 1 to the 2n plus 1 power gives me a constant 1. So I'm left with, for my numerator, just negative 1 to the nth over 2n plus 1, summing from 0 to infinity. So here, pi over 4 can be represented as the sum of this alternating series. So if I were to multiply that sum by 4, we get an expression for pi, which is known sometimes as the Leibniz formula for pi. So we see in this example, this gives another application of why we might care about power series. It will allow us to possibly find the sum of other types of series. So in this last example, the series that we had here is an alternating series. It is not geometric, it's not telescoping, So thus far, we weren't able to find the sum of a series unless it was alternating or telescoping. But here, we were able to find the sum of the series is pi over 4 if we're able to think about that series in terms of a power series of a function evaluated at some point. Now let's look at our last example. In this last example, we'll see another application of these power series representations of functions. So here we are asked to consider the integral of 1 over 1 plus x to the fourth with respect to x, which is similar to the problem we saw a little bit earlier in this lecture. Now, none of our techniques of integration can be used to evaluate the antiderivative of this function. We can't use a substitution or partial fractions or a trig substitution. None of those methods work here. So instead, we could evaluate this integral by thinking about it in terms of a power series. So let's see how to do that. My first step would be to express our integrand, 1 over 1 plus x to the fourth, as a power series. And to do that, we could rewrite it in the form of the sum of a geometric series. That is 1 over 1 minus negative x to the fourth, which would be the sum of a geometric series from 0 to infinity of a, which is 1, times r, which is negative x to the fourth to the nth power. Or equivalently, the sum from n equals 0 to infinity of negative 1 to the n times x to the 4n. And we can do this as long as the absolute value of that ratio, which was negative x to the fourth here, is less than 1. So equivalently, the absolute value of x to the fourth has to be 1, so the absolute value of x has to be less than 1. So in order to evaluate this antiderivative, that is 1 over 1 plus x to the fourth dx, we are integrating the power series we just found. So we will have some constant, c, plus the sum from n equals 0 to infinity of negative 1 to the n, and then the antiderivative of x to the 4n is x to the 4n plus 1 divided by 4n plus 1. So this would be an expression for that antiderivative. Since we don't know what the antiderivative is, we can't solve for our constant using some initial condition. We would have to know what the antiderivative was as a function itself. Now, in the next part of this problem, we are told to use a power series to approximate the value of the definite integral of that same function from 0 to 0.2 or 1/5, and we need our approximation to be correct to within 6 decimal places. So let's think about how to do this. We're trying to evaluate a definite integral from 0 to 0.2 of our function, 1 over 1 plus x to the fourth dx. Now, in order to do this, using the fundamental theorem of calculus, we would need to find an antiderivative of this function, which we said was of the form shown here. Now, since this is a definite integral here, my constant of integration c is no longer needed. So I would be looking at the sum from n equals 0 to infinity of negative 1 to the n times x to the 4n plus 1 all over 4n plus 1. And I'm evaluating from x equals 0 to x equals 0.2 or 1/5. So evaluating this at the endpoints, we have the sum from 0 to infinity. And let's see what we get when we plug in our 0.2, or 1/5. So I would have for my numerator -1 to the n. If x is 1/5, then I have 1/5 to the 4n plus 1, or I can think about that as division by 5 to the 4n plus 1 power. And then I still had my 4n plus 1 from the denominator. And then we would subtract what we get when we plug in 0 for x. But since this is a power series centered at 0, when you plug in 0 for x, the whole thing is 0. So we have the following series, which is an alternating series for the value of this definite integral. Now, to approximate the sum of that series, which would be the value of this definite integral, we can use a partial sum, say the nth partial sum of that alternating series. But I need to know how many terms to add in order to approximate to within the desired accuracy. In this case, we need accuracy to within 6 decimal places. So any time that we're talking about the accuracy in a partial sum approximation of an alternating series, we need to use the remainder estimate for an alternating series. So let's start by saying by the remainder estimate, for alternating series, the error in an nth partial sum approximation is given by the absolute value of the remainder, r sub n. And the remainder estimate for alternating series says that that would be bounded above by the n plus 1 term of my series if we neglect the alternating sign. So here, my n plus 1 term would be given by 1 over, plugging in n plus 1 in place of n, I would have 4n plus 4 plus 1, so 4n plus 5, and then 5 raised to the same power, 4n plus 5. So in order to have the desired accuracy, I would take the expression for this maximum error, that is 1 over 4n plus 5 times 5 raised to the 4n plus 5 power, and I need it to be less than whatever accuracy bound I'm given. In this case, we need accuracy to within 6 decimal places. So I need this maximum error to be less than 1 over 10 to the 6th. So now let's see if we can solve this inequality for n. If I take the reciprocal of both sides, I would have 4n plus 5 times 5 to the 4n plus 5 power has to be greater than 10 to the 6th. And if we start choosing values of n, integer values, starting at 0 and moving upward, we see that the first value of n for which this is true is 4. So we need n to be at least 4 to approximate the value of this definite integral to within 6 decimal places. So what we find then is that this integral of interest can be approximated by the sum of the first several terms up through n equals 4. So looking at the series that we have here for that definite integral, to approximate the sum to within 6 decimal places, we start by adding the term where n equals 0. So we would have a 1 over 5. Then plus, when n is equal to 1, we get negative 1 over 5 times 5 to the 5th power plus when n is equal to 2, we have 1 over 9 times 5 to the 9th power. Then for our next term, we have a minus 1 over 13 times 5 to the 13th, and then plus 1 over 17 times 5 to the 17th power. So that last term corresponding to n equals 4. So the sum of these first terms would be an approximation of the value of that definite integral, which is correct to within 6 decimal places. So in this last example, combining a few different topics that we've talked about throughout chapter 6 thus far.